So I was finishing off on Janine Cole's fully 3D model of the Bushveld complex, which she developed, and Patrick Cole's software called Pygmy, which is Python gravity and mag interpretation. So it's freely available, and it's worth looking into that if you're doing gravity and mag modeling. It doesn't do inversion yet, I don't think, but it does do forward modeling, and it's very easy to use, and it gives you a chance to make quick and dirty forward models. One of the big problems with 3D forward modeling, especially in potential fields, is once you get your model set up, it's very hard to change it, as I think Steph will attest with IGMAS. It becomes a real nightmare to try to change things. So if we carry on here, next one. Or is it not going forward? Okay, there we go. So part of what we looked at was Carol Finn then looked at the northern lobe in great detail. And one of the issues is the northern limb is shown outcropping here. I need to go get my laser pointer so I can, ink color, where's arrow options visible? Where's the laser pointer now? This is, oh, it must be an older version. Okay, so I'll just keep it as an arrow. Okay, so the northern limb has always been a bit enigmatic. It's outcropping over here, and then there's this little patch up here in the north part called Villanora. But there's this huge shear zone to the north of Villanora, and there's also this area up here, which has now been shown to host Bushveld material. So all the way up into here is prospective, even though the gravity high ends about here. So there's a lot of speculation about how far west does the northern lobe go. And the work that Carol Finn did, well, the older models, obviously Duplessis and Klavect in 1987, there was a paper in SAJG that demonstrated, as far as their modeling concerns, they were able to show that it only extends less than 50 kilometers into the interior. And they made a very big point of that, saying that there was no way it goes further to the west than about 50 kilometers from the outcrop. And in fact, it shallows off very, very rapidly. But they did not take the MOHO into account. They only modeled down to about 4 kilometers. And the gravity high is directly over this thickest part. So that makes sense. That's the way gravity works. And in fact, in this southern part over here, where we have the feeder zone, they actually get quite a bit thicker. These are very, very simplistic models because they were just hand calculated. So what Carol Finn was able to show, and a lot of Janine's modeling also showed, was that if we start accounting for the MOHO and we do these longer profiles and we incorporate other data such as the magnetotelluric data, we can see here is the crustal thickness, for example, by Nair, and crustal thickness by Youssef et al. In 2012. Both of them show quite a bit thicker crust under the northern lobe, and that allows us to have the northern lobe mafic rocks of the Bushveld complex extend all the way over to here, which is about 200, close to 300 kilometers apart from the eastern outcrop. So this whole area is now prospective, and it's a real question as to why this lips up at the edge here on the eastern side. And the question is, what depth is the petering out on the western side? So that'll be an interesting exploration target. And this is the model, some of the models that Carol Finn produced. This is in Oasis Montage, and you can see she gets a very, very good match. We have this feeder zone, which is a fairly high density. We have the upper zone rocks, which are shown here in green, and the main zone shown in the other green. And finally, the low critical zone and lower zone in the blue. Now, she's not able to extend the critical zone and lower zone all the way through. These are north to south profiles, and this is the southernmost profile. this one's west to east, but it's not clear how this might be able to actually come up over here. Cap 59 is a magnetotelluric station with a 1D MT model location. So these are some of the other profiles that Carol was able to produce and get fairly good matches with. And we can certainly see that the main zone and the upper zone extend well across the entire region of the northern lobe. So the size, the modeling, the magnetotellurics, and the teleseismic results support the model of an extensive northern lobe extending approximately 150 to 200 kilometers to the west of outcrop. Sorry, I said 300 earlier. I was misspoke there. And the gravity modeling suggests there's a feeder zone at the TML, particularly near the region of Polokwane. So the connectivity statement would be the Bushveld complex is connected at depths from west to east, both in the main chamber and in the northern lobe. So how can we solve this question? Well, the most obvious thing to do is a big, long seismic line across the Bushveld complex. And really, the country should know what resources it has. This would really, I would consider to be baseline exploration that allows the companies to come in and know what they're getting into, is to have some kind of a baseline seismic line across the entire Bushveld complex to really help clarify what could be there at depth. And unfortunately, at this point, even though there are a number of seismic lines that are published and known about, none of them really extend across the entire region, either the northern lobe or the western to eastern lobes. So the Witz Seismic Research Center is becoming the go-to place for all of the seismic data. Moose has done an amazing job getting all of the seismic data from a variety of different companies, both in the Witz and in the Bushveld complex, into the research center for use by students and even consulting from corporate researchers. This is just a shot of some of the Witz data, not even the Bushveld data, but you can see the Witz data extends well beyond the Witz basin itself. And there are many, many seismic lines. This is the Bethlehem lobe that people were investigating. So there's a tremendous amount of data, and this isn't even all of it. So let's look at some of the data that's in the Bushveld, the 2D seismic lines. There's two research lines over here in the far western lobe. And then there's a small seismic line up here in the northern platinum mine. There was a line here that actually extends further, but the data appear to not be available at the moment. This was published by Jeff Campbell, and it investigates a gravity high. There is a seismic line number 3 and number 4, which were shot by the Council for Geoscience as part of the geophysical surveys that were done in the late 80s. So let's have a look at some of these. This is the one up here, seismic line number 1 on Northam, and it was very much a proof of concept. Would it be possible to see seismic? A lot of the oil industry felt that hard rock seismic would never work because you don't get the velocity changes that you do in the oil industry. But the density changes in the Bushveld are especially good for getting reflections. So we can see here, even in this kind of crappy reproduction, that you can see the reflection at the Marinsky Reef at the base of the main zone. And down here, we can see things in the Pretoria group and the Transvaal underlying the Bushveld complex. Another seismic line here was seismic line number 2. This is the one that Jeff Campbell looked at. And this is a longer version of it. And you've got what was of interest was that over this part of the seismic line, which is way up here towards where the granites are outcropping, is a gravity high. And the thought was that the Marinsky or the UG2 could have been displaced upwards and might be at mineable depths. So the idea was to investigate the gravity high using seismic to see if perhaps they were brought up closer to surface. And they were, certainly if you trace this down dip to where they would be at a much lower level. And so they have been uplifted a tiny bit, but you can see that it's actually a very, very complicated section. And it actually will look like the section in line 3 when we look at it. This same kind of hump appears and some complicated structural features here. And this is really where I think the work is going to be done over the next couple of years, is trying to understand how much of this complicated type deformation is related to emplacement, post-emplacement, and if any of it has been brought closer enough to surface to actually mine. So the third seismic line we'll look at is this one here, coming up north from Pretoria. You can see it's still quite a ways from seismic line number 2. And we get this same kind of gentle fold here. So this is line number 3. Not much, this is the basis for Terry Odger's MSc thesis, which he completed back in the early 90s. And you can see you get incredibly good reflections close to Pretoria, where a lot of the information or a lot of the lithologies are outcropping, and they continue through here. It gets a little bit more vague, but we do get this kind of humping up here along this part of the section. But it could benefit from more modern processing. And finally, line 4, if I just come back up here, here's line 4 up in the northeast. I think Stephanie has worked on this a little bit, and a few other people have also looked at it. But the only thing really published on it is this sketch of what's going on. And you can see disruptions in the Transvaal. This fault is probably affecting the Transvaal more completely than it shows here. There's quite a bit. This is very much a preliminary interpretation. You've got the Rustenburg layered suite coming through here and actually continuing on the other side of the Wonderkop fault and the Malope Dome. So those are just some of the seismic lines that we have. Stephanie's working on an interpretation of a seismic line down here that crosses over the Bethel lobe and into this very, very complicated region where the eastern lobe and the Bethel lobe actually join. And there's this Moloto borehole that actually gives us mafic rocks of the Rustenburg layered suite a little in from the edge of the Bushveld complex itself. So here's a very early compilation of that seismic line. In fact, it's not even the whole thing. It's only the part from A to G, showing you how complicated it is. I'm sure Steph has a much better version of this at this point, but you can see how incredibly complicated it is and how hard it's going to be to sort out what is really the Rustenburg layered suite, what is the Transvaal, and possibly even what is the Witz down in this portion of the seismic line. So lots of fertile work there. This is showing this line up here in the northeast, which Terry Odgers looked at very, very briefly. And there was a USGS publication on this based on Fiona, I think it was Fiona Stevens' work, not Fiona, I've got the name wrong, but anyways, for her work up here, unfortunately, this is going east to west. So this point is this point over here. You've got quite a bit of Transvaal coming up through the Bushveld complex, but you do seem to have a full sequence on either side of this Transvaal dome. So 3D seismic has also had some really exciting research done on it. This is from the Modiqua mine that Anglo-American has in the Eastern Bushveld complex, and it's one of the most detailed seismic surveys, 3D seismic surveys ever conducted. It had a geophone spacing of 2 meters and a shot spacing of 5 meters, if I remember correctly, and shows incredible detail. There's some very major faults coming through here, and there's a number of magnetic dikes coming through also. But some of these dikes were not really imaged very well. And so the interpretation they preferred included both the seismic data and the magnetic data. So it's important to realize that both of these can be beneficial especially in a detailed survey like this. This was in the area of what they called the bowl of spaghetti, where all of those magnetic dikes are coming through this region. So I moved on then to some paleomagnetic studies. This was a photo, one of my favorite photos taken by Janine Cole. This is myself and Carol Finn. We're actually looking at her PowerBook, looking at the magnetic image of the data connected to, there's actually a GPS. So we're doing this in real time. Our location is being shown on the computer screen. And our colleague over here, a geologist, is actually out looking at the rocks. So kind of summarizes some of the things that go on. So the magnetic data were collected with the this amazing Midas system, which was one of the early horizontal gradient systems that collected incredibly detailed data. They were able to fly this as low as 30 meters above the ground, because you can see the terrain clearance is based on how high the vegetation is. And in this area, they've got fairly low vegetation. So this is a very impressive set of surveys. Anglo has collected data all throughout the Bushveld where they have properties. And the data we're talking about is up in here. And in fact, that highly detailed seismic survey was up in this region, this so-called bowl of spaghetti, where we have these very magnetic dikes and a large number of them. So the physical properties were determined through some of the boreholes. And this is just to set the scene for some of the magnetic dikes. You can also see over here the so-called Pilansberg age dikes, which are shown in this blue color because they're obviously magnetically reversed. And you can see this Sheneng structure, which is a huge structure just south of Pilansberg. This actually continues right across the country. And we'll have a look at some of the paleomag work on this set of dikes. So here's an example of what you can see on some of the aeromagnetic surveys. You can see faults. This was determined to be a fault by some of the offsets found around it in the lithologies. You can see a hint of that up here. There are dikes. These are some of the Pilansberg dikes, which are negatively magnetized. So they actually carry strong remnants. And you get ultramafic, iron-rich ultramafic pegmatoids shown here in this deep blue, which also indicates that you get some remnant magnetization with those. You also get, you can see some striping here. A lot of this striping is due to the topography and the effect of flying down off the edge of a fairly large fault, a fairly large topographic feature. And you often get that even in cleaned up magnetic data, you will still see some effects from topography. You can also, there's a couple other cultural features we can see here. Some roads, I'm not seeing them right away, but we'll see them in, they're in this next image. Okay, oops. Sorry. Okay, so this image shows, for example, a slimes dam, the edges of the slimes dam, and a railroad track. Okay, we get this beautiful string of pearls effect along the railroad track, and we can see some of the communities in this area. This is near the area where we did our 2005 field school. This is that large Sheneng structure, and you can see how it offsets some of the Pilansberg dikes. Although not completely, it's unclear what's going on here. And the, you know, the cultural features show up really, really well in this particular map. So part of what Sean Letts did was look at this area. This is now in the northeastern part of the Bushveld complex. And he looked at these dikes, which at the time had always been thought to be Karoo age because of their orientation. They appeared to be coming out of that triple junction, but Sean was able to date these dikes and showed that they were quite a bit older than we thought at 1.8, which is the approximate Waterberg age. So you've got a whole series of dikes coming through here, and he sampled quite a number of these. This was his MSc. You can see here some road structures. So this beautifully straight line is associated with construction and road structures. This is the Hartsbergite that is associated with the Merensky Reef. It's just below the Merensky Reef and can be used as a tracker horizon for it. These are very subtle structures that appear to be possible fault zones. And you can see, again, the road coming through here and an IRUP down here. And you can see actually several generations of dikes coming through, some stronger than others. This may just be, for example, a change in the susceptibility values along the strike length of the dike. And you can see this kind of an echelon emplacement of dikes that is very well documented here. Again, an echelon emplacement. So what did Sean find? Well, here's a really quite an interesting example. The blue line here is aeromag over a particular profile. So let's say somewhere here on this magnetic dike. And surprisingly, when you go to the same spot in the field and you walk over that feature with the ground magnetometer, you actually can show that it's comprised of or comprising 3 separate dikes. So you could probably get some of that with downward continuing the aeromag data, but this makes the point that it's worth looking at your aeromag data in even more detail and actually doing some ground truthing on it, because you might have written off this whole area because you think that this dike is super wide and there's no platinum at all. But it turns out there's Merensky and UG2 in between these 3 separate dikes. So you can constrain the size of these dikes much better from the ground survey. So the age of the dikes is about 1.9 GA, much older than we previously thought. So the value of the aeromag data and the ground magnetic and the dating is to help with the mining on the ground. The aeromag gives us an idea of where things are very complicated, and the ground data gives us much higher resolution insight into what the dikes actually look like. So he was able to publish his work in Geophysics Journal International. We got some geochronology and some paleomag. And I want to take a moment, actually the point I want to make with this is to just point out that the result of the paleomag and the age dating of these dikes demonstrated that they were the same age and that the dikes had recorded a magnetic reversal. So the fact that some of these dikes are positive and negative is the effect of the magnetic field of the Earth at 1.8 GA actually reversed direction during the time of emplacement of these dikes. And these dikes were emplaced over a period probably not exceeding 1 million years. So fairly tightly constrained. So that was the results that were reported on in this paper. And then in 1998, Hatting published kind of a summary. Hatting is a South African geophysicist who did a lot of paleomagnetic studies, largely concentrating on the Bushveld complex. And he did a lot of his work in the early days of paleomag. And at that time, it was a very, very slow procedure. And one of the things they did was estimate when to stop demagnetizing their results. And the result he got, this 1998 paper is a summary paper of all of his results. And we can see Bushveld complex critical zone way up here, almost near the 10 degrees north paleopole line, and then pieces of the Bushveld complex main zone, Bushveld upper zone, Bushveld main zone, northern limb main zone, et cetera, et cetera. All these poles were found from his Bushveld work, and they represent almost, quite a huge range, almost 50 degrees of paleomagnetic movement through the time period of 50 million years of emplacement. And that would have been 50 million years of emplacement based on the ages at the time that Hatting was working on this. We now know that the Bushveld was emplaced probably in less than 1 million years, although more recent dating is suggesting another controversy about the age of emplacement, and that the critical zone may actually have been in place at a different time. And that, I hope, is one of the controversies that Rice will talk about, is some of the age dating issues that are coming up, but certainly not over a period of 50 million years. This would be fairly fast paleopole motion, even for a 50 million year emplacement. For a 1 million year emplacement, this is ridiculously fast. And so this was the motivation that I used to suggest that Sean relook at the paleomag poles of the Bushveld complex itself. Is this contradiction between the paleomagnetic results, which suggest a huge range of motion, which would suggest, more than 50 million years of emplacement, and the actual age data that suggests only 1 million years. So if we plot it in a different way, these are Hatting's 1998 Bushveld poles. We've got the critical zone way up here. We've got the northern limb way down here. You can see this is, over 30 degrees of latitude, and that takes quite a bit of time to move. So what Sean did was he invented a way to actually collect paleomag orientated cores underground. He used a laser pointer and a very clever system of trigonometry to link with the surveyed pegs in the underground mines. And he was able to get a huge number of samples underground. And the reason for doing that is we know that a lot of the outcrops, well, just about any outcrop in South Africa, will be affected by lightning. And in these older rocks, it's so important to make sure your data are good and that there are no alteration effects and no effects of lightning. So a lot of the samples that Sean got were from mines, from the upper zone, the main zone, both in the eastern and western main zone and in the critical zone. So you can see here he's got a good distribution both geographically and stratigraphically throughout the Bushveld complex. And when he reduced all his data and looked at it, we end up with basically a single paleopole for the Bushveld. So all that spread has now coalesced into a single pole, and these all overlap and give us a single pole for the Bushveld complex, which makes more sense with the age data that we were getting that suggested everything was in place within 1 million years. The other thing he found were a number of magnetic reversals. So one of the things he did was look at, was the Bushveld in place horizontally? And he was able to show with a fold test that the Bushveld was in place horizontally. And also Hatting had a similar result, although Sean's is a little bit more robust. He had quite a few more samples. And so then the question is, well, when was the dip of 10 to 30 degrees made? And was that as a result of actual isostatic adjustment? Or was that some deformation? Or is this another controversy that we need to look into a little more carefully? He also showed that there was a single pole in support, which supports the age data better. But he also found 7 reversals within the Bushveld complex. And he's plotted these here on the western and the eastern lobe on the very basic stratigraphy. We've got critical zone, main zone, and upper zone here. And we can see down here in the critical zone, we see 2 samples that show reversed, and then a sample that shows normal. And then as we cross over into the main zone, we have a reverse sample, normal, reverse, normal, reverse, normal. And so when we first interpreted these data, what we looked at was, we said, well, if we think about things like the Deccan traps, we get pulses of material into that are in place. And probably the oldest materials at the bottom and the youngest materials at the top. And so we can look at the reversals in that way and assume that the age of these magnetic reversals correlates with the age of the layering, which would probably be the oldest at the bottom and the youngest at the top. And so that was kind of our interpretation, documenting 7 magnetic reversals from bottom to top. But then Grant Cawthorne and I were discussing things at tea one day, and I was, kind of bothered about this because I wanted to understand more about the cooling of the Bushveld and what constraints we had on that. And Cawthorne and Walraven had written a paper in 1998 looking at the cooling of the Bushveld itself. And what we did was combine this cooling information or this cooling modeling with the magnetic reversal modeling. So you can see here we've put an intrusion into the crust, 2 kilometers thick. We have the roof and the floor. This is a very simplistic model of the Bushveld, and you can see it splits the geotherm over here. This is the geotherm shown here, and it splits that when this intrusion goes in. And we have time on the x-axis and thickness on the y-axis. So over time, as we go along, we're going to see how this changes. So, sorry, time equals 0 here, and now time equals 6,000 years, and we get this cooling effect. We heat up both the roof and the floor, and we develop cumulates along the floor of the Bushveld complex. And finally, at 180,000 years, we have deformed the geotherm both in the roof and the floor, and the heating of the rocks has changed this geotherm, and the cumulates have accumulated across this whole segment of 8 kilometer thick emplaced material. Sorry, the x-axis here is temperature, not time. Apologies. And so if we take these curves through time and look at them, so here is our age, our cooling curve at 280 million years after the Bushveld's in place. Here it is at 380 and 480 and 580 million years. We see that as the Bushveld cools, it intersects the Curie temperature of 580 degrees in 2 places, because it's cooling from the top and the bottom. And so if a magnetic reversal happened at this time, it would be recorded both at the top of the Bushveld and at the bottom. And so by mapping this out, we were able to demonstrate that it's possible that some of these magnetic reversals are actually repeated, so that the reversals up here are the same as some of the reversals down here, R1 and R1. So that had important implications in terms of where these reversals were located. Sorry, I want to go back here. This has big implications, not just for the Bushveld complex, but for any intrusion that's large enough to cool over the time scale of a magnetic reversal. So if an intrusion takes more than 200,000 years to cool, which is the approximate mean time of magnetic reversals, then it's possible to record the same magnetic reversal at the top of the intrusion and at the bottom. And so that was really the main reason that this paper got into the journal Geology, was because it has global implications for the cooling of magmatic chambers. Okay, and so further work is what we are working on now. And in fact, the exciting piece of equipment that we got downstairs yesterday, that we brought into the physical property lab. I hope you saw the photograph. is what we want to do is find where exactly these magnetic reversals are located in core samples. Now, the Bellevue core, which we have access to, is a little bit too disjointed to actually be orientated. But one of the things we plan to do with our new core from the ICDP project is run it through this new metal cylinder that will allow us to record the orientation of the magnetic field rapidly and look for changes in the magnetic field which would be associated with magnetic reversals, and try to find those in a rapid manner in the core so that we can find where in the stratigraphy we need to study these reversals. Now, one of the things that's exciting about this is one of the problems in exploration in the Bushveld complex is that in the main zone, it's very difficult to figure out where you are on the magnetic maps. And if we could actually find this magnetic reversal, these two magnetic reversals, where they occur in more detail in the stratigraphy, then that would give us a marker horizon for a very sensitive magnetometer, such as the squid magnetometer, to use as a marker in the main zone. And there's some question about how well this would work, because the reversal is related to the cooling, and the cooling is related to the thickness. If the Bushveld is thin in a particular area, it may have cooled faster, and so that may adjust where this magnetic reversal occurs, and we may be able to use that information to determine where the Bushveld's thinner. So cooling, accounting for the cooling from the top and the bottom means the magnetic reversals may be the same ones recorded at the top and the bottom. So anything that cools on the same time scale as magnetic reversals, such as about 200,000 years, may exhibit repeated reversals at the top and bottom. So how can we use this even further? Well, one of the things I'm very interested in is the paleo intensity. There has been a tremendous amount of controversy in the last 3 years about when the solid inner core formed. Now, you may remember there were also some articles about the inner core being anisotropic. The seismic data actually shows that it could be faster on the north-south than the east-west. And it's not only anisotropic, it may have a faster hemisphere and a slower hemisphere in a horizontal sense also. So there's tremendous interest in the solid inner core, because all of these structures that we're seeing with the seismic probably relate to how did the solid inner core grow. And there was a paper in Nature, 3-4 years ago, that suggested that the solid inner core actually only formed at 750 million years ago. Now, this has huge implications in terms of Earth structure and how the magnetic field is stabilized. It's more stable when you have a solid inner core, because you're able to develop these tangent cylinders, which are constrained by the solid inner core and allow you to develop these magnetic field lines, which are quite strong. And so paleo intensity studies allow us to study how the Earth's field changes through time. And this is just a summary plot of some of the age data and the actual paleo intensity studies that have been done. And some of these are not very high quality. They were done back in the day, and there's a lot of controversy about doing paleo intensity studies on old rocks. And so if we clean the data up and look at the best data, we see there's a huge gap in the data at around 2 billion years, which is right when the Bushveld occurred. And it turns out the the work that Sean Letts did shows that the paleo intensity data from the Bushveld is some of the best data that we have, because the paleo intensity or the paleo mag information is held by these tiny single domain crystals of magnetite that are encapsulated in the plagioclase crystals. So they are extremely stable. They really are some of the best data we have. And so what I've been doing with my Blue Skies project is to try to fill this gap in with paleo intensity work on single crystals of plagioclase. So we've Grant Bobby's student Ilton, I've forgotten his name. Sorry, he has developed a way of extracting single crystals of plagioclase from a thin section, and we're looking at a couple of other methods to extract these. And we can actually orientate these crystals if we're very careful how we do this procedure. And so we can not only do paleo mag, we can do paleo intensity on these. And our preliminary study that we were able to do just before COVID struck showed that we are able to get very good results from single crystals. And so moving forward, the plan over the past year was to actually do this work, but I'm hoping to be able to go to Oxford in November, December time this year and work on these single crystals of plagioclase to get paleo intensity data from 2 billion years ago. And so that will help us understand when the inner core formed. Okay, so I just want to mention a little bit more of Janine Cole's work. She's done this beautiful overview of the magnetic signatures of the Rustenburg layered suite, where she's looked at a variety of high resolution magnetic surveys that the Council for Geoscience has collected and characterized using, here's an example of a small part of the magnetic grid, and she's done the geological interp and shown you what is causing the various anomalies within that. So this is a really nice summary of looking at a variety of different parts. And the reason for this was trying to model the magnetics in the Bushveld was really difficult because there's so many different types of signature. So by systematically going through this, she was able to characterize the different lithologies and the different types of situations that were causing the magnetic anomalies. The development of the squid tensor magnetometer is an ongoing joint venture between Anglo De Beers and the Jena Research Institute in Germany. This is an extremely sensitive, I think it's an order of magnitude more sensitive than your rubidium, your more normal, there's cesium vapor magnetometers or rubidium vapor magnetometers. This is yet still an order of magnitude more sensitive, and more importantly, it's a tensor measurement. It's actually a tensor measurement. So just like we have gravity tensors, there's also magnetic tensor instruments. And there's a huge race on worldwide to really get this commercially viable. And the problem boils down to vibrations. It's actually very difficult to stabilize the platform enough to remove the vibrations at a level that takes advantage of this increased sensitivity. So these are two of the different platforms that they've been experimenting with, flying it in a bird or attaching it to the helicopter. And so I just want to summarize some of the work, most of the work, well, a lot of the work. We continue to do more work, but after emplacement, the Bushveld appears to cool from the top and the bottom. The time frame is about 680,000 years, which is well within the time frame of magnetic reversals. So since that's a similar time scale, we suspect that the magnetic reversals that we have could be from the top and the bottom. And we hope that our paleo intensity studies, as we pull apart these magnetic reversals in detail, will be able to confirm that. Thinner areas will cool faster and may appear out of sequence of the thicker areas, and the reversals may provide a proxy for thickness. And we may be able to find reversals from subtle changes in the declination from 3-component magnetometer data. That's the work of Bill Morris. He's been working on that for a number of years and has shown, certainly in some of the data he has, that he is able to easily find these magnetic reversals. And in fact, in some of the Bushveld data, we have a preliminary indication from some of Obone Zapato's work that this may be the case. So I'll leave it there. We continue working on, Mfana is working on the Bellevue core using the data from the Council for Geoscience, combining the susceptibility data that we collected and curated and the hyperspectral scanner data. And we look forward to our ICDP project, which is coming up, and we are starting to get good news all around. We've had a couple of funding applications approved, and so we'll be moving forward with that project.